Today we discuss one important topics related to homogeneous linear differential equation with constant coefficient. Okay, homogeneous linear differential equation. Okay, we'll discuss these topics now. Also, previous day we also discussed about that. Now we're going to further discussion of that. Okay, so we start from this. For a real number s belongs to R. Okay, we also known about another real number e to the power s. Okay, where e is the unique number, where e is the unique number. Okay, e is the unique number, and obviously whose natural logarithm is 1, whose natural logarithm, okay, natural logarithm is 1. Understood? Then what happened? Then obviously we know about that e to the power s plus t equal to e to the power s e to the power t, okay, and e to the power minus t equal to 1 by e to the power t. Okay, for any real number, for any real number s and t. Understood? And in this way we also define another one. Okay, so define here. What happened? Let c equal to a plus ib. Okay, let c equal to a plus ib be a complex number, okay, with real part a, with real part a, and obviously imaginary part b, and imaginary part b. Okay, then what happened? Define e to the power c equal to e to the power a cos b plus I sin. Okay, then what happened? E to the power ib equal to what? Cos b plus I sin b. Understood? Is called the Euler formula. Okay, is called the Euler formula. Okay, Euler's formula. Then we also see about that. If we erase our portion and going to further discussion of that, then what happened? We write in this way. Here c equal to 2 plus I pi by 3. Okay. Then what happened? E to the power c equal to e to the power 2 plus I pi by 3 equal to e to the power 2 to the power I pi by 3 equal to e to the power 2 here cos pi by 3 plus I pi sin pi by 3 equal to what? Equal to e square. Cos pi by 3 equal to what? Here obviously 1 by 2, and here root 3 by 2. Understood? Then what happened? We study this one, 1 plus I root 3 by 2. Understood? This one is the result, equal result, e to the power c equal. In this way we also discuss this function. Now it is the whole portion and going to further discussion of that. Okay, in this way what we obtain, we write it in an definition. Okay, we write here the function f, okay, r to c defined by R to C defined by if t equal to e to the power ct for a fixed complex number c. Okay, for a fixed complex number c is called an exponential function. Is called an exponential function. Understood? Then we obviously, that means we're going to discussion further. Okay. Here we write one theorem related to that. Okay, for any exponential function, for any exponential function, for any exponential function, if t equal to e to the power rt, okay, then if dash t equal to what? Then if dash t, sorry, e to the power, here we see, right, c, okay, then if dash t to c to the power ct, for c belongs to c or r, anything, okay, some constant, be a constant. Understood? Then what happened? Then we're going to discussion another, that means one first order equation. Okay, that means an equation of first order. Okay, an equation of order one. Okay, is of the form, that means one differential equation y dash plus a0y equal to 0. Understood? This one we mark as star, and then going to discussion another theorem related to that topic. Okay, we write here theorem and going to discussion about that. The solution space for star. The solution space for star is of dimension 1. Each of dimension 1. Okay, and has e to the power minus a0t is a this as a basis. Okay, the solution space for star is of dimension 1 and has e to the power minus t0t as a basis. Okay, now we're going to prove of that. We erase our portion and going to prove discussion about some proof related to that topics. Okay, we write here proof and then going to further discussion of that. Okay, here clearly stars has e to the power minus a0t is a solution. Okay, now we suppose that xt is any solution. Okay, here we write suppose that okay, xt is any solution, okay, of star, xt is any solution of star, then what happened? Then x dash t equal to, okay, minus a0 xt for all t belongs to r. Understood? and then define what? Define zt equal to e to the power a0 t xt. Okay, then differentiating z else, okay, or gives what happens z dash t equal to what? E to the power is 0 t here x dash t, okay, or this dash and xt plus e to the power is 0 t here x dash t. Understood? Then what happened? Then this one equal to a0 e to the power is 0 t here xt plus e to the power is 0 t x dash t. Understood? Then this one equal to what? That means x dash t equal to, we know about that, this one e to the a0 t x t difference e to the power a0 t here x dash t equal to a0 x t. Okay, then this and this difference equal to 0. Not a problem at all. Okay, so z dash t equal to 0. Then this part happened. Then what we write here, then z is z, since z dash is identically 0, so z is a constant function. Okay, so we write it here, since z dash is identically 0, then z be a constant, okay, function. Z be a constant function. Then what happened? Okay, if z be a constant function, then what happened? We write it in above. We erase that portion. Okay, then there exists. Then there exists a complex number k. Then there exists a complex number k. Okay, such that what? Such that zt equal to e to the power a0 t here xt, okay, equal to k for all t belongs to r. And so what happened? So xt equal to k e to the power minus a0 t. Okay, then this one is doesn't xt equal to this one. So we conclude that any solutions to star. So we conclude that any solution, okay, to star is a linear combination of okay, e to the power minus a0 t. Not a problem at all. Okay, so here we stop now. That means we also discuss one simple uh, theorem related to that first order differential equation. Okay, and obviously we also discuss e to the power function and Euler formula. Okay, now we also going to discuss one corollary related to this theorem. Okay, so we write it now. Corollary: for any complex number, c, for any complex number c, okay, the null space of the differential equation, the null space of the differential equation of the differential equation null space of the differential operator. Okay, here d minus ci has, okay, has e to the power ct as a basis. Okay, has e to the power ct as a basis. This one is, that means too easy. Okay, one operator, differential operator, and the null space of this contain e to the power ct as a basis. Okay, so this one is not a problem at all. We also discussion about that. Okay, so what we discuss now, we write it in this way. That means give him an nth, okay, give him an nth order homogeneous linear differential equation, nth order homogeneous linear differential equation, differential, okay, homogeneous, given an nth order homogeneous linear differential equation, okay, with constant coefficient, with constant coefficient, okay, with constant coefficient. Can we write in this way, y to the power n plus a n minus 1, y to the power n minus 1, okay, plus that dot 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 a1 y1, okay, plus a0 y equal to 0. Understood? Then what happened? It's auxiliary polynomial. We erase our portion and going to further discussion of that. Okay, we write it here. It's auxiliary polynomial. It's auxiliary polynomial. Okay, B. Its auxiliary polynomial b pt equal to what? Pt equal to t to the power n a n minus n e to the power n minus 1 dot dot dot, okay, dot 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 what? A1 t plus a0, okay, this one with the auxiliary polynomial and factors into a product of polynomial, factors into a product of polynomial, okay, factor into a product of polynomials of degree 1, of degree 1. Then what happened? That is pt equal to t minus c1 here t minus c2 dot 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 t minus cn, okay, where c1 c2 cn are complex number, where c1 c2 dot 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 cn are not necessarily distinct, okay, not necessarily distinct complex number, complex numbers, okay, understood, not a problem at all. That means its auxiliary polynomial, this one obviously factor into a mm, polynomial of degree 1, okay. Then what happened? Then we also see pd equal to, okay, so it is lower portion and the discussion of that, okay. That means pd equal to what? Okay, here we write, then thus pd equal, thus pd equal to d difference c1 I, okay, and d difference c2 I dot 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 d difference cn I, okay. Then what happened? The operator d difference cii, okay, commute. Then we have, okay, so we have what? N of d difference cii here subset of n of PD, nullity of PD. Okay, that means nullity of this operator is subset of nullity of PD. Okay, since NPD coincide with the solution space, since NPD nullity of PD coincides with the solution space solution space of, okay, of given differential equation, of given differential equation. Okay, so we also discuss this one now. Now we're going to write one theorem related to that topic and obviously give one example. We erase that portion and going to further discussion of that. Okay, I think all are understand this. Now we erase that portion and going to further discussion of that. We write it in above, write theorem. Okay, here let Pt be the auxiliary polynomial. Let Pt be the auxiliary polynomial. Okay, for Pt be the auxiliary polynomial for a homogeneous okay linear differential equation. Homogeneous linear differential equation. Okay, homogeneous linear differential equation with constant coefficient. With constant coefficient. Okay. Then what happened for any complex number C? For any complex number C. Okay. For any complex number C, if C is 0 of PT, if C is 0 of PT, okay, then e to the power ct, then e to the power ct is a solution to the differential equation, solution to the differential equation. Okay, understood? This one is not a problem at all. So just we'll talk about that. Pt be the auxiliary polynomial for a homogeneous linear differential equation, and obviously for any complex number c is the 0 of pt. Okay, then e to the power ct is the solution of differential equation. For pt, how that means pt equal to what? Pt equal to t difference c1, t difference c2, dot 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 t difference c1. All are different, they're not necessarily all are distinct. Okay, in this way. And obviously then what happened? In this way we will discuss this one, and pd equal to, we know about that, we write it here. Pd equal to, that means in this way, d minus c1 here, d minus c2, and dot 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 d minus cn. Okay, equal to what? Cn I, sorry, c1 I, c2 I, cn I. Okay, then what happened? Obviously we write it here. That means y to the, this one is y to the power n plus a n minus 1 y to the power n minus 1 dot 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 a1 y dash and a0 I. Okay, sorry, a0 y equal to 0. This solution also we construct from this from pd, and this one is part of pd and then pt. Okay, now we also going to discussion about that one example related to that topic. Okay, so we erase that portion and going to discussion one example. We write here example and going to further discussion of that. Okay, given the differential equation, given the differential equation, okay, what given the differential equation y double dash difference 3y dash plus 2y equal to 0, okay, then what happened? It's auxiliary polynomial. It's auxiliary, okay, polynomial, polynomial b what? Its auxiliary polynomial b pt equal to here t square difference 3t plus 2, okay, that means t difference 2 t difference 1, okay, then what happened? Then obviously hence we see that hence e to the power t and e to the power 2t be the, okay, be the solution, be the corresponding solution, corresponding solutions, okay, corresponding solutions to the given differential equation, corresponding solution to the given differential equation, to the given differential equation, okay. Then we also discuss in this way what happened is here, that means since, that means the solution space of differential equation is a subspace of C infinity, we write it in here, since the solution space, okay, solution space of the differential equation, of the differential equation, of the differential, okay, equation is a subspace of, is a subspace of C infinity, okay, then what happened? Then span of e to the power t, e to the power 2t, okay, is linearly independent, is linearly independent, okay, understood? This one is not a problem at all. That means since the solution space of the differential equation is a subspace of C infinity, then the span of e to the power t and e to the power 2t is linearly independent. And then this one, e to the power t and e to the power 2t, okay, e to the power t, e to the power 2t, okay, big is a basis, okay, for the solution space, is a basis for the solution space, okay, for the solution space, understood? Then what happened? Then obviously we see that then we find a basis for the solution space from the given differential equation, okay. In this way we also discuss this theorem related example, we also discuss, okay. I think this one is too easy. Now we're going to discuss another theorem, but we not prove today, just write this theorem now, okay. Theorem, that means statement we write, and then going to prove in further class. We write this statement now. Here statement is that, okay, for any differential, for any differential, for any differential operator PD, operator PD of order n, of order n, okay, the null space of PD, the null space of PD is an n-dimensional subspace, is an n-dimensional subspace of C infinity, okay. Then I think this one is, we stop here, okay. The null space of PD is an n-dimensional subspace, okay, of C infinity. Then for today we stop here. Okay. Now we're also going to further discussion uh, with these topics later. Okay. Because this topic is too vast. Okay. So discuss later further one. Today we just discuss so easy topics. Okay. Just exponential functions, Euler's formula, and obviously related to solution space for first order differential equation. And then we also discuss solution space for differential equation. Okay, which is equal to the null space. Okay, that means null space of PD. Okay, and obviously if PD factor into linear factor, okay, then obviously this one nullity is subset of nullity of PD. Okay, in this way we also discuss these two easy portions, and obviously we write it in this theorem way. The null space of PD is an n-dimensional subspace of C infinity. Okay, that means we from null space we take any vector. Okay, then this one is obviously is an the null space is an n-dimensional subspace of C infinity. That means we take any vector from this null space, then this one obviously infinite times differentiable. Okay, this one is today we discuss. Okay, and today we stop here. If you get this type of video, please subscribe my channel. If you want to give like, please click on like options. If you have any questions, comment, suggestions, write it in comment box. So I stop here. Thank you.